Aren't there also like privacy screen protectors? Do they work in the same way where it's like seeing it from one angle, you can't really see someone's screen, but if you look at it head on, then you can see it just fine?
I'm trying to think. I know I've looked at some of these, and I think the way they work is they essentially work in the same way. They're just really big LCD screens. So there's just a massive LCD screen with like a liquid crystal in between two sheets of glass, which have polarizers. And depending on whether you were applying or taking off the current, because obviously if you just switch one of the polar filters through 90 degrees, then you can change whether it's on or off that makes it go black.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And before we get started, just wanted to mention that we have released material science merchandise for those of you who want to support us or just express your passion for MSE. You can check out more of the designs at itsmaterialworldpodcast.com/shop or by clicking the link in the description. All right, let's get right into it.
Today's sponsor is MatMatch. With MatMatch, you can find materials for your projects in their free database of thousands of metals, polymers, composites, and ceramics. For example, you could search based on a given mechanical property, such as hardness or tensile strength, or simply search by name to find more information about a specific material. You could also find and contact suppliers if you have questions about a certain material, and join more than 2 million engineers and designers who use MatMatch every year. To join, simply go to matmatch.com and start searching for free today.
Hey everyone, we are very excited to introduce today's guest, Dr. Marty Jopson, a science TV presenter, communicator, and self-proclaimed science geek. Marty has been involved with science television in many different ways over a 20-year span, from presenting to prop building to directing, producing, and more. He also performs hair-rising science on stage at science festivals across the UK, and he's authored 3 books, including The Science of Everyday Life and The Science of Food. On the topic of everyday life, we have brought on Marty to discuss the materials found in your smartphone. So we're very excited to have you, Marty.
It's absolutely my pleasure. Thank you for inviting me along.
Absolutely.
Awesome. So yeah, we're really excited to talk to you today about materials in our smartphones. But first, we are really curious because we haven't really talked to anyone who's in science communication. So what drew you to this field? And since it's vital for everyone to develop as a good communicator if they want to be successful, what advice do you have for young scientists or engineers about effectively communicating or effectively telling a story?
So that's quite interesting, actually, that you used a word there that's very key. You used the word story. Because that's what communication is about. It's about telling stories. And I realized that that was going to be the thing that I liked doing. Many years ago, I did a PhD in, it's actually in plant cell biology. I'm a plant cell biologist by training, but that was so long ago, it's slightly irrelevant, really. And at the end of my PhD, I realized, actually, this is not going to be my thing. I'm not going to be a research scientist, but actually I'm quite good at telling the stories of science, and I'm quite good at that communication bit of it. So I went off and became a science communicator, and that was more years ago than I care to remember. And ever since then, I've been, as you say in the introduction, thank you very much, I've been doing all sorts of things, and it all falls under the same category. It all falls under science communication. And that's about telling stories. And if you're a sort of an early stage scientist, whatever that is, whether that's an engineer or a research scientist or whatever it is, then learning to tell stories is how you learn to communicate. I mean, I can talk about that for hours just on its own, but I mean, the very basics is, and probably one of the most important things is you've got to learn when you can and when you can't sort of step outside your comfort zone, and when how much do you need to know to be able to talk about stuff. And one of the things that you often hear when you talk to people, if I do training in communication stuff, which I do quite a lot of, people say, oh, I can't talk about that, I don't know about that. Well, I'm here on a material science podcast, and my scientific training is in plant cell biology and microscopy. But I know, and I've picked up enough, and I talk to people about material science all the time. I know more than they do, and that's all you need to know to be able to tell the story. And then it's about learning how to tell the story, how to structure a narrative, and how to get that across in a kind of an entertaining way. There's a lot to it, shall we say. It takes practice. And I mean, basically, you just need to get up there and do it. Some people are great at it. Some people get it. Some people struggle with it. But, the more practice you have at this sort of thing, and you go and watch people who are good at it and learn from other people who can do these things. Those are my top tips. So, yeah, don't be too precious about your science, just get in there, talk to people, practice and learn from others. Those are the things I would do.
So, Marty, how do you then balance the idea of like backing up your story with data and proof versus just like explaining the why? Because I know that's a big thing in science communication specifically.
You have to be a generalist if you're going to be. I mean, some people who go into science communication, they talk about one thing, it's the thing they're good at. You get the standard sort of, the professor that goes off and becomes a TV presenter or something. They have a speciality, and they will do that thing, and that's what they become known for, and they continue kind of in the research side of things. But for someone like me, I'm more of a generalist, so I have a very broad understanding of science. I always was a generalist. The PhD was an aberration, quite frankly. I studied all sorts of things. I studied material science at university. I studied physics and chemistry and maths and weird things with the medics, pathology and stuff like that. But it's being able to talk about a broad range of things and having a breadth, and then having an interest and being able to sort of, understand that stuff. And if you've got that breadth, then you can usually, especially if it's the general public, you can talk to them with a degree of confidence. And it's about understanding. And, sometimes I take my talks. I remember I do a talk all about microscopy, and I'm talking about, this is mostly biological microscopy. And I ended up at one of the Europe's biggest microscopical congresses, talking to them about it. And that's fine. And it's just about finding where your information can overlap with that audience's interest, I guess. And then, presenting that without kind of making stuff up, which can sometimes you make mistakes and you get corrected at the end of a talk, and you're like, fine, that's fine. That's okay. I've made a mistake. I will learn. You get somebody coming up to you afterwards and saying, yeah, you said that thing. That's not true. And you go, okay, note to self. And then you check it afterwards. Because, just because somebody tells you it's not true doesn't mean it's not true.
Yeah, true.
And so were you always this good at public speaking? I think that almost most scientists and engineers I know go into engineering because they don't have to talk in front of lots of people.
Yeah.
So I guess could you explain were you this good, or if you weren't, how'd you get this good?
I wasn't. No, I was kind of the fat shy kid at school who did all the sciences. It was really good at science and kind of, was top of science. That was my kind of thing, the nerdy kid at school. And then I went off and realized that there was sort of more to it than that. And I enjoyed, kind of being, telling stories and being, and then I ended up, just tried out doing science talks at a science centre where I was doing my PhD in Norwich in the UK, and I just liked it. And it's about having the confidence to be relaxed in front of an audience, and then the rest is kind of history, which is quite complicated, but it's there. I went off and did a lot of telly stuff behind the camera, ended up in front of the camera, and did a lot of stuff in the UK on sort of the primetime telly stuff. And it's about honing a craft in the end. And I call myself a performer now, primarily. That's how I think of myself. I'm a performer. But I'm just talking about a very specific thing. But it's the same, when I the sort of people I look to that inspire me these days are, street artists, people, juggling on the street, and you can see them and you can learn from those guys, or people on stage, and, artists on stage, there's all sorts you can learn, and you can bring that into the communication. But how you get good at it, well, some people do and some people don't like it. And, sometimes it's just a matter of what you're good at naturally, and knowing that that's what you're good at and doing what you're good at.
That makes sense. Cool. So
it's not particularly helpful, because sometimes I know that people, they're like, you must go out there and talk in front of the crowd. I don't want to, I hate it. But sometimes, and we have to accept with each other that sometimes there are people who are better suited to doing that, which is why I have a job, because people come to me to say, can you be the front man for our project? And I'm like, sure, what's it about?
Yeah, that's awesome. Yeah, it's about pushing yourself out of your comfort zone, and maybe we'll do that to a certain extent as we get into the materials in your smartphone. But since we'll start with the general stuff, and we'll break it down by each subsystem, starting with the phone screen. So I was just wondering, can you talk us through the type of glass that is used in smartphones and how this may differ from other glasses in other applications like construction or packaging?
So the glass on your phone screen is quite specific. There's a thing called Gorilla Glass. I don't know if you've come across this. This was, I think it was Dow Corning actually invented it. And it's a fairly standard aluminosilicate glass. Aluminium silicate glass. We'll sort of put it in the middle of the Atlantic, shall we? What it was actually Apple went to them and said, what we need a glass that's going to be really scratch resistant, but also flexible enough that it's not going to break in half immediately. You put your phone in your back pocket and sit down, and cost effective and all these sort of things. So they came up with Gorilla Glass, which has been copied subsequently by other people. And basically what they do is they take a standard glass and they immerse it at sort of hundreds of degrees. I think it's like 400 degrees or something, Celsius that is, in liquid alkaline potassium bath. So molten, I assume it's potassium hydroxide or something, molten potassium hydroxide. And then what happens is you get exchanges between the sodium and the potassium ions. You get potassium in the surface, which then increases the volume essentially, because potassium's a bigger atom, so that you get an increased volume. So you get pre-stressed glass at the surface, which gives you basically toughened glass, but on a very, very thin sheet, which you can't do otherwise. So that's what makes the glass. I'm just looking at I've got an old iPad here. I'm looking at it, and it's, despite being ancient, it's not actually got any scratches on it. It's about the only thing that hasn't broken on it. Everything else has, but the glass is fine. And we all know, it does shatter if you sort of whack it properly, but it's really remarkably tough when you consider sort of what it goes in your pocket with keys and stuff like this, and it comes out fine. So that alone is a fantastic piece of material science. But then you sort of go into the screen, and the screen itself is made of like dozens of layers. There's like layer upon layer upon layer of material in there. I don't know, where do you want to go next with the screen? I guess that's the question. Do you want to go into the touch sensitivity of it, or just the liquid crystal? You choose.
Yeah. I want to go back to when I think I was like in middle school and I got my first phone, and the touch screen was cutting edge back then, but it was absolutely terrible. Could you kind of talk to us about maybe what technology allows like touch screens with capacitive touch, and maybe if you know a little bit about it, has improved quite a bit since I was younger, so we'd love to hear about that next.
Yeah, I mean, the very first touch screens before your time, I think you'll find, were literally, they were kind of like two sheets of plastic with thin wires, and when you touched them, it literally, where you touched, it made the wires connect. And that was how you knew. And it had like a terrible resolution, because obviously you couldn't put too many wires in, because otherwise you couldn't see what was on the other side. And that's the problem. That's actually one of the key problems with touchscreens, is ultimately it's an electrical, thing. It's detecting the touch through electricity, but it's got to be see-through at the same time. And most electrical conductors are not see-through. In fact, it's a sort of a basic thing. If you think about things that are naturally just straight clear, acrylic or glass, they are not made of metal elements. They're made of non-metal elements. And it's down to some of the specifics of the electron, structure of the different atoms that means that some things that are transparent tend to be non-metals. So having a conductive material that's also see-through is quite a challenge. And the way we get around it is these days we use a thing called capacitive touch. So that's using it turns your screen into essentially millions of capacitors. So a capacitor is, it's a very simple electrical component. It's basically like a sort of a battery that kind of almost instantly charges and discharges. And what you're doing with your phone screen is, as anything moves towards the phone screen and gets close to it, doesn't have to touch it even in some cases, but depending on the sensitivity, they have it turned down so that you do actually physically touch it. That changes the capacitance of a specific spot on the screen, or at least it allows us to detect that there is a change in capacitance at a point. And that's what we're picking up. And the only way we can do that is by having see-through conductive materials. And the one that everyone uses is a thing called indium tin oxide. So this relies on an element, it's about 75, so 3/4 of indium tin oxide is indium. Indium is it's one of the metals. It's just below gallium, so aluminium, gallium, indium. It's just in that column. It's what can I tell you about indium? It was discovered in the let me just see if I can get this right. I think it was 1860 something by a couple of Germans. It's called indium because the color in spectra is, there's a bright indigo line in the spectrum. I always assumed it was from India. Because it was discovered in India. It's not. Although, of course, the word indigo comes from India because that's where the indigo dye came from originally, which is why it's called indigo. So it kind of goes back to India one way or the other. But anyway, it's a relatively unusual element, but it's fairly abundant. It's about the same as silver. Anyway, so indium tin oxide takes the slightly unusual properties of indium, because indium is sort of on the edge of being a non-metal. It's sort of close to that boundary of metalloids. And if you add to it a little bit of tin and make a very thin coating and make it into an oxide, it's conductive, but very see-through. It's got a sort of a very high transmissibility, so it allows a lot of light through it. So we can coat glass with it, and they vapor coat it. So under vacuum, they create a vapor of indium tin oxide, and that then settles onto the surface. And then what they can do is you can etch it with a laser. So you can etch it to create all the kind of the fine detail that you need. And that allows us then to create this capacitive touch system that we can detect exactly where you've touched the screen. There are alternatives, but they're not as good. Aluminium zinc oxide is the one that people tend to use otherwise, but it's quite sensitive to moisture. So if liquid or humidity even gets in, it oxidizes or reacts with the moisture, and it loses its transmissibility and conductivity. And it doesn't etch so well. So indium tin oxide is still the go-to at the moment. There are alternatives. Graphene is quite an interesting alternative, but that's still, going to be quite a while, I suspect. But yeah, so that's how we do the capacitive touch with this funky combination of elements, indium tin oxide, which is one of the great things about, the mobile phone. It's got these really unusual elements that you don't really see anywhere else actually in them. So that's capacitive touch for you.
That's awesome.
Yeah,
go ahead, David.
Yeah, so I think we've all been to a store that has like an iPad or something, and it just doesn't line up where you touch it. Is that a failure of like the system reading the different points like incorrectly or the capacitance incorrectly? Or is that maybe some of the material has started to oxidize due to some of the errors that you're talking about?
That's a good question. I suspect, I mean, the obvious answer is that it's some sort of software problem,
Like
and
a
that it just needs
calibration.
kind of recalibration.
Mhm.
But it could be, because the way I understand it, it's originally you had literally kind of vertical lines of indium tin oxide strips and horizontal strips. And then by detecting the changing capacitance between, it was, strip number 642 and row number 326, and that gave you a point on the screen. But now they don't do that. They have a better system which detects kind of the capacitance based on its distance from the corners, essentially. So it's possible that those detectors then go wrong. It shouldn't oxidize or anything, so it shouldn't chemically change unless you've done something horrible to them. And if it's just sat in a shop, then it probably just needs a reboot, quite frankly, let's face it.
Interesting. Cool. Okay.
So with the water resistance property being like more and more important in phones, I was just wondering, like, in what situations would that alternative of like I think you said aluminum zinc oxide be used?
That's right.
Is
yeah.
Is it just being, is
I'm
it like
not
a
aware
cost
that
factor?
it's all I know is that it is a transparent conductor.
Got it.
System, but it's not being used in phones, and I think there are too many problems with it. I think actually what seems to kill it is the laser etching, because obviously it's all well and good sort of with the early systems, which were pretty crude, but these days you need such fine detail building into the I mean, I guess it's a printed circuit board, isn't it? It's kind of like, it's not a printed circuit board, but it's an etched circuit board. So you're layering this stuff on and then etching some of it away to create your circuit board, your see-through circuit board on glass, which just blows my mind. That
that's fascinating.
Amazing. And I think that's actually one of the restricting factors at the moment. I mean, there's other technologies to say. I mean, graphene's the one that everyone gets excited about. And it's one of those sort of 5-year technologies where everyone says, 5 years. And then 10 years later, you ask them and they say 5 years. And I've heard that from several people, over the last 15 years. So I've yet to see graphene. But graphene's really good because it's also very flexible. Indium is pretty flexible, so you can put it on a flexible plastic sheet. I've got some, and you can just bend it backwards and forwards, and it seems to be fine. So yeah, graphene's the sort of the big hope for that.
Oh, gotcha. Yeah, I've seen new generations of phones being like foldable. So yeah, I think
well, all of that. I mean, then then you get into sort of hinges and things like that, and gosh, how you do that.
Right.
That's quite tricky, that
is. Yeah, the whole 5-year thing is nanotechnology in a nutshell. But so I guess we can now move on to, like you mentioned, the layer by layer, and we can talk about LCDs or liquid crystal displays. I remember
crystal.
Yeah, I just remember looking at our phones like through microscopes in our lab classes, if you remember, David, and seeing those red, green, and blue pixels. So I was just wondering if you could explain the science behind all that.
Yeah, I mean, LCDs are fiendishly complicated, actually. So I'll try and do this briefly, but basically it relies on polarized light. And that's the first thing you've got to get your head around. So I'm going to jump to the assumption that people know what polarized light is, and that light has, is a wave. I mean, it's a particle as well, but let's not go there. It's a wave, and it can have a directionality. It can have, you can have vertically polarized or horizontally polarized. And what you do is you take two polarized sheets and you cross polarize. So you put one at 90 degrees to the other. So the first sheet, light passes through it and is, say, vertically polarized. The second sheet it hits is horizontally polarized, so no light goes through it, so it's black. So you observing on the other side see nothing through it. Now, if you put something crystalline between those two sheets, something weird happens, because crystals, if they're the right thickness and the right sort, so sucrose is particularly good, sucrose works really nicely, it causes the polarized light to twist as the polarized light goes through the ordered array of atoms. And you get, if you get it right, a 90-degree twist. so that if the light goes through vertically polarized, then through a crystal, it becomes horizontally polarized, and then through the next polarizer, it goes through the next polarizer because the next polarizer was horizontal. So now you can see light coming through because the crystal bends it. So what you do is you put in a hydrocarbon in the gap between your two polarizers, which is a liquid crystal. And basically, all that means is they're hydrocarbons that have three elements to them. Top element is a rigid, flat sort of structure made from benzene rings. And that will arrange itself, if just left on its own, into a sort of a crystalline array because it's sort of got a structure. And then you've got a wiggly tail at the bottom, which is the bit that makes it liquid, I guess, and not very polarized. And then at the top, you have a charged particle, usually a nitrogen or something like that. So you put that in between your polarizers. It forms a crystalline structure, so light can pass through it. Or rather, when light goes through it, it twists, which means that your sandwich polarizers crystalline, liquid crystal, and then another polarizer, light passes through. Now, if you now apply a voltage to that liquid crystal, because it's charged, it messes up the crystal structure. So the whole thing breaks down and suddenly it goes black because you've messed up the crystal structure and the light's no longer being twisted. So now what you have is you have essentially a light shutter that you can turn on and off with a switch, right? Mm-hmm. So what your phone has is at the back, right at the back of the screen, there is a flat LED, right? It's quite a complicated structure in itself, but anyway, it's basically a flat sheet of light that's on permanently, which is, by the way, why it doesn't matter what you're showing on your screen, it drains the battery really quickly because that light is on. The whole screen is illuminated. And then over the top of that, you've got millions and millions of tiny little shutters that can be individually opened and closed by just applying a current. And of course, to get the current to the individual shutters, you need a see-through conductor, which can be laser etched. So we're back to indium tin oxide. So indium tin oxide is crucial for that as well. Some ways more so even than the capacitive touch. So you now have a sort of an incredibly complicated series of shutters. You can turn them on and off individually, and you've got a screen. The color that you're seeing, as you said, when in your lab, when you look at it, is basically on top of that. There's another layer, a sort of a printed out layer of different elements that give you the color filters. And the elements they use there's some crazy things in there. There's like dysprosium, praseodymium, europium, terbium, all sorts of like really crazy rare earth elements that are used to create those colors specifically. And that's the screen. I mean, just that alone, that bit of your phone is the most fantastic, taken together, a sort of a sandwich of many, many layers. The most unbelievable technology goes into that. And the material science alone there, the different elements that you're using, and each one is there for a specific reason.
Yeah. Wow. Yeah, I didn't realize that. Like, I understood like the polarization and everything, but I didn't realize that we always had the light on. I thought that they could have made something to like maybe keep it off more, but no wonder my phone keeps on dying.
Yeah, that's good. And it's also why if you look at your phone and you're wearing polarized sunglasses, it just doesn't look very bright because the light that's coming through is polarized. The light that you're looking at is already polarized. And if you turn the phone through 90 degrees, it quite often becomes brighter or darker one way or the other. So you can sort of move your phone around and you get another kind of cross-polar effect going on. So you have to take your glasses off to be able to see your phone properly. Well, I do, but that's just me. That's my age.
Yeah, my favorite application of polarizations with like sunglasses, like you were saying, that they can be polarized, and you can test whether you have polarized glasses or not if you have one, and then you just put them 90 degrees to each other, and it's basically just a larger version of what's happening in your phone. And if they're both polarized, then you can't see anything, but if only one is or neither are, you can see through both. So I think that's just a really cool, like blown out version of what's happening like a million times on your phone screen right there. I guess.
I mean, this is why I got into this subject, because so what I do is I do a sort of a talk about material science. But actually, what happened was I was given, because I'm a Zeiss ambassador, so I work with Zeiss, who make microscopes, a German company who make these amazing microscopes, and I was doing all this stuff on plant science and biology, and I wanted to do some stuff on material science. So I upgraded my microscope so that I could do polarized microscopy, which is beautiful and fantastic, and used in a lot of material science applications, because you can tell a lot by looking at the reflected, usually the reflected for material science, the reflected polarized light, by just putting some cross polars in. But you can also do it, and there's all sorts of things. I mean, as I say, sugar's really nice. Aspirin crystals give fantastic effects through cross polars under a microscope. Wow. But yeah, it's a really good, simple thing to show people, and it's interesting. Something that always gets a ooh-ah if you show an audience. I've got these two really big sheets, sort of A4 sheets of polarized material, and you just hold two up in front of you, and then just rotate one, and it goes black. And people just, it blows people's minds when they see that, because it just is an amazing thing. And then you have to explain. It's quite difficult to explain. I hope I did that sufficiently briefly, but not without jumping too many steps.
Interesting. Aren't there also like privacy screen protectors? Do they work in the same way, where it's like seeing it from one angle, you can't really see someone's screen, but if you look at it head on, then you can see it just fine?
I'm trying to think. I know I've looked at some of these, and I think the way they work is they essentially work in the same way. They're just really big LCD screens. So there's just a massive LCD screen with like a liquid crystal in between two sheets of glass, which have polarizers. And depending on whether you were applying or taking off the current, because obviously if you just switch one of the polar filters through 90 degrees, then you can change whether it's on or off that makes it go black. But if that makes sense, if you think about it. So you can have these sort of massive sheets, and then you just kind of press a button and it bink goes dark. Or they can use them I've seen a system where you can by just basically putting on a piece of polarizing filter that's cut to a shape of a logo, for example. You can press a button and a logo appears on a sheet of glass. You press another button and it goes off. So you can have multiple ones if you're clever. You can do all sorts of clever things with it. But.
Wow.
Cool. All right. Well, yeah, that was really great about what goes into the screen. It's so complicated, and there's so much technology that we don't even see, because that's the purpose. If we saw it, then it wouldn't work. But moving on, the next area or subgroup that we want to talk about is inner electronics. So elements like gold, silver, platinum, and tungsten are often used in the wiring in the circuitry of the phone. What properties make these metals the optimal choice, despite we all know how much gold and silver cost, but platinum and tungsten are also very expensive as well?
Yeah, it all comes down to, often with this, it comes down to sort of, obviously you need something that's super good at conducting electricity. You want something that's a really good electrical conductor. And most people just assume that, it's a metal, it's going to be good at conducting electricity. And that's not true. Not all metals are equal in their ability to conduct electricity. Gold, silver, these are good metals at conducting electricity, and copper's the other one that's obviously really good, but it does oxidize. And, the noble, metals, gold and silver and platinum, the reason we use them is because they don't oxidize. So, especially for connecting, the really fine components, like your, stuff within microchips, and basically soldering microchips to the substrate that they're then sitting on, so they can then, communicate with the rest of the circuit board. That needs to be super fine and super conductive, but also not degrading in any way, because even the tiniest amount of degradation of performance will impact what's happening, because they're so tiny. So they've got to be sort of perfect and stay perfect, which is why we tend to use those. And things like tungsten's just like super high temperature stuff, generally speaking. So if it's going to get hot, you don't want it degrading with any temperature stuff. So that's where that comes in. But generally speaking, that's where we're using those precious metals the sort of traditional precious metals like gold and silver, and they get brought in for that reason. So it's as simple as that, and the fact that they're really good conductors.
Got it. And so speaking of tungsten, one thing I wanted to briefly discuss is the idea of conflict minerals like tantalum and cobalt that are mined in nations with just awful working conditions. I was just wondering if you could speak to this more and maybe give your thoughts on ways that we could potentially build a more ethical supply chain.
Oh gosh,
that was a loaded question.
Make it easy for me, why don't you? So yeah, there's a thing called conflict elements, and basically a conflict element is, or a conflict ore, as in ORE, is something that is mined in an area of conflict, and the mining of which is used to fund that conflict. The example I often go to is, I hesitate to say it's my favorite example because it's not something anyone should have a favorite of, but is tantalum, as you mentioned. So tantalum is super important in capacitors. It makes the best capacitors. Just because of its electrical properties, it makes the best capacitors, and all the little capacitors that you have on a circuit board, they're teeny tiny little things, surface mounted components, will have tantalum in them. 60% of tantalum produced currently in the world, it comes from an ore that's mined out of the ground with a bunch of other things, and it's actually quite difficult to extract, but it comes primarily from the Democratic Republic of Congo and neighboring Rwanda and Burundi. And if you know anything about Africa, you'll know that the DRC, the Democratic Republic of Congo, has had a horrible civil war raging for, gosh, I can't remember how long it is. It's just been going forever. It's, decades or something horrible like that. And I think it's currently the most deadly conflict on the planet, by which I mean more people have died in this conflict that is taking place currently than anywhere else. And both sides of the conflict are using the mining of tantalum ore as a source of income. Hooray! That makes everyone feel better about everything, doesn't it? So, what do? We need tantalum for all our electrical devices because we need capacitors. We could find tantalum from other sources. There are other places you can get tantalum ore. I mean, that's one of these things, this is to do with, where these resources actually sit. This is geopolitics now we're talking about. You could just go and find it somewhere else. But clearly the stuff that comes out of the ground in, Congo, in the DRC, is probably the best source of tantalum, and it makes it economic. So that gives us an economic incentive to get it out there. Of course, if we just stopped if we said, no, we're going to boycott this, we're not going to take it from there, well, ultimately that also impacts the people of the DRC and the surrounding areas, because, whilst it is funding a conflict, it's also funding people's lives. This is people's, bread and butter, and it might be horrible conditions and stuff, but it's still their only job, and they're presumably getting paid something for it. So it's difficult. There isn't an easy answer. I'm sorry, there isn't. I don't have a magic bullet here. One of the answers is that we need to create a circular economy. We need to have a donut economy. We need to take the tantalum that's already in the system, so to speak, the stuff that's in your mobile phones right now, the stuff that's in your computer, and not throw it away and not put it back in the ground. We've already dug it out once. Let's keep it in the system. Let's find a way to be, economical about this. And the obvious way to do that is to not throw it away in the first place. To, it's the old reduce, reuse, recycle. So, send it to somebody else. Recycle your electronics. Do you need that new phone? Do you need that new computer? If you do, well, make sure your old one goes to somebody else who can use it for a bit longer.
From the recyclability standpoint, since there are just so many different elements in your smartphone, like how easy or difficult is it to be able to recycle the components of it?
It's really difficult at the moment with phones. And there is a lot of pressure at the moment from all sorts of groups to really move towards a sort of a joined up sensible. I mean, it just makes sense, doesn't it? I mean, why would, I mean, I'm looking over here at my iPhone. The battery's a bit knackered. It's not a new iPhone. I've had it for quite a while, and I'm constantly charging it. You know, it doesn't last a day without having to recharge. And we all know, you're both shaking heads. Yeah. You know, we all know this. We all have this. And iPhones are the worst culprits at this, because at least most Android phones, you can just pop the battery out and put a new one in. I don't know if you've ever tried changing a battery on an iPhone. I once did this with an old iPhone I was giving to one of my kids. It was terrifying. You had to sort of prise the screen up at a kind of a worrying kind of screen, bend it up and get a kind of a plastic doodad that they sent me in a kit and kind of prise this thing off. And it was just, I was terrified that any moment now the whole thing was going to just shatter into 1,000 pieces. And then the screws, you get these tiny screws which are like dust, which are literally like some sort of little puff of metal that you could just breathe a little heavily and it disappeared into the carpet and you never find it again. And it was just terrifying. And there's, as you well know, there's a sort of a cottage industry out there of people changing, iPhone batteries, which completely nullifies all your warranty, but it's the only way you can upgrade your battery. So wouldn't it be good if somebody they put a screw on the back that you could undo that enabled me to change the battery? Wouldn't that be great? Wouldn't it be great if we could have a phone where, I could pop the camera out and just pop a new one in when they develop a new camera, or a chip set, just take out the chipset. And actually, if you open up a phone, a lot of stuff you can sort of dismantle a bit, and you can pull out the little connectors and you can unscrew things. And, and there are moves, again, there are kind of, there are people pushing to have systems which are, upgradable, self-upgradable. And the dream is to have a phone where, you just literally, you subscribe to a package and, they send you the new chipset once a year and you just pop it open and pop the new chipset in and send the old one back in a self-addressed envelope. And they, use it to build phones for somebody else, that's what we should be doing. We're not. So the best you can do is at least recycle your phone rather than chucking it away. Or worse, just leaving it in the drawer and not doing anything with it, because then it becomes redundant. And, you've just wasted 2 years of its life by having it sat at the back of your drawer. Sorry, I'm preaching.
Yeah, you bring up a lot of good points. I think that multiple questions. I'll start with my first one is, when we talk about these complex minerals, tantalum, tungsten, cobalt, if you go up to a random person on the street, I would almost guarantee that not everybody knows where they're from or what they do. So as science or engineers, and especially maybe as you're a science communicator, how do we bring about light into these materials or minerals that no one has ever heard of before, really?
You do what I do, which is I go and talk to people about this stuff. I go and, tell people the stories about these, what's in your phone, and you've got to make it grabby, because if you sort of say, I'm going to give a talk about kind of why we're all doomed, you probably get a few, but you won't get many. You won't get many people coming to that talk. And if you're trying to talk to, say, a younger audience as well, you've lost them already. You've got to make your message interesting, but at the same time, you can approach these things. Even young kids are willing to hear this story, especially these days. I go and talk to primary school kids about this stuff, and I just make sure I'm not too kind of heavy on it. I don't want to, depress them all and have them all, doom laden when they go home. They want to have fun. They want to see something they remember, but you can just drop in a little bit of the message about, circular economy and recycling stuff. But these days, especially, as everybody's so kind of aware of what we're doing to the environment, whether it's sort of climate change, or whether it's what mobile phones and what we're doing to sort of digging things out of the ground. I think it's a story that people want to hear. So you've just got to find a way to tell it that isn't too dreadful, basically.
Yeah.
And by that I mean, obviously, hopefully you'll tell it well, but it's just got to be a story that people are willing to sit through. Because if you're gonna, let's say you're gonna put a YouTube video up, you're doing a YouTube thing. If you put a video up that's just all doom and gloom and terrible, depressing statistics, well, who's going to sit through that? But if you make it fun and interesting and drop some of this stuff in by the by as part of the story, then that's how you sell it to people.
Gotcha.
As they say, you got to sell the sizzle.
Yeah, you have to fulfill their desire to feel in addition to their desire to learn as well. But
Exactly.
You have
Yes.
to like balance that without being too heavy, like you mentioned.
Yeah.
That's a tough line to walk.
Yeah.
And the second question I had for you is that I remember reading in class about like a modular phone, but again, going back to what you said earlier, that kind of seems like a 5 years thing where they'll get to it in 5 years. But I guess like going into it, as consumers, like Apple is knowingly making it harder for us to repair the phone and creating this really complex warranty so we can't go around them. I guess, is there really much we can do as consumers, or how do we like paradigm, because it's only getting harder. They're only making tinier screws. They're only making it harder to get to the battery. And it's seeming like they want to do it so you spend more money and not care about their recyclability at all.
I think the general move is towards where we want to be. I think, if we talk about, okay, where I want to be, I want to have that modular phone. So I don't end up with a phone that's sort of only partially usable, because I have to carry around every time I go out. I have to carry like not one, but usually two kind of spare batteries just to plug in. So I want that, but I still like my Apple. I'm wedded to Apple. I'm I'm a full Apple fanboy. I'm sat here with an iPad. There's a brand, I've just upgraded my MacBook and I've got an iPhone here. So I'm wedded to Macs, but by the same token, I would love them to be even better than I think they already are. And I would jump on that opportunity. So what do we do? I mean, you can communicate the problem, which is what I do in my own small way. You can legislate the problem. I mean, in the UK, in the EU, they've just legislated for a commonality of charger legislation, so that basically USB-C will now become the standard charger system. The idea being that it means you don't need to always buy with every product you buy. You just don't need another charger pack, so that you could just use the old one.
Yeah.
So you just don't need, because every time I buy a phone, I get a new charger. Great. Well, I don't really need that many chargers. But I think I've got a drawer full of them. So there is that sort of thing as well, sort of legislation and pushing, your legislators to do that and to bring that sort of stuff in. But that's really difficult because you're pushing uphill. But, we can see now that the big tech companies are beginning to hear, what people want, and it's going in the right direction. I think it's just going to take 5 years, like everything.
Cool. All right, on to the final section of the inner electronics. One of the most critical parts of the phone itself are these silicon chips that play such a large role, and as it's considered the brain of the device. What characteristics make silicon such a unique, effective material within our smartphones?
So silicon, sits in a very special part of the periodic table. If you look at your periodic table, or you sort of conjure it in your mind, you have you've got the noble gases on the right-hand side, and then immediately next to the noble gases, you've got your non-metals, which kind of sort of form a triangle at the top, on the top right, and then to the left of them and below the diagonal of the triangle, you're into metals, and then you're over to the other side. You're in through the transition metals and lanthanides, actinides, and then you end up with the alkali earths at the other end. Anyway, the point is that diagonal line between the metals and the non-metals, you get what are known as metalloids, which is a horrible word. I should have come up with a better word than that. Metalloids, metallish. I don't know. But anyway, and they kind of it's a bit fuzzy, the line. If you look at it, it's not a nice, neat. It's not like some things on the periodic table. It's not kind of like, kind of a nice, neat row diagonally going at 45 degrees. There's sort of, it kind of bibbles up and down and summering, and depending on which version you look at, sometimes some elements are included and some not included, and so it's a bit vague. But these are elements that have some metallic properties and also some not metallic properties. The key one being electrical conductivity, how conductive they are, and silicon sits in that group. So it's just below carbon, and because of that, it means, and because it's just below carbon, because it can make the number of bonds you can create sort of linked crystal structures. But by adding in other metalloids, you can change its conductivity. You can sort of turn the conductivity on and off. And it's just like with our little, with the LCD, you need to be able to turn on and off things in a computer using electricity. And with silicon and a bit of cunning, if you go back, so you can basically make a switch that you can turn on and off with electricity. And it's because of its sort of adjacency to the metals, but also the non-metals. It's because it's in that gap between the two that we use that. And if you look at the other things they use to dope silicon chips, they use, what do they use to dope them with? They use things like, so you've got silicon, you use things like antimony, gallium to dope them, and they're all in that same group of metalloids, metallish elements. So it's really, that's all it comes down to. They have that very specific property.
And what exactly does doping do, or like how does it improve it?
Oh, I have to haul that out of my head. Doping is all about whether or not you have sort of extra electrons or electron holes, so vacancies for electrons. And then it's about, by applying a current, you can essentially move electrons or the holes, it gets a bit fiddly, between different parts of your layered system. And again, it's about kind of creating these very fine layers, which are laid down photographically, that allow you to build up individual transistors, electronic switches. And then, obviously on a microchip, you've got, God, I don't know how many they fit on these days. I'd have to pull up Moore's law to check it out, but billions probably of individual transistors that then give you your processor.
Got it. Yeah, I remember our classes with like n-doped and p-doped semiconductors. So
yeah, I must admit, it's one of those things I'd have to look it up again just to refresh my memory. It's been a long time since I looked at that.
But anyways,
I wanted to talk about that in front of an audience, sort of as part of a stage show, as part of a performance. And it's really hard. It's just really, really hard to do anything that doesn't just become a slideshow with a lecture, which I didn't want to do. So I avoid it. I avoid talking about it because it's just too complicated in some respects.
Yeah,
or just a bit too dry, maybe.
We have like whole classes designated towards it, so trying to explain it in a minute is a tall task.
If you're studying it, then I can't. That's your own fault. You have to.
Okay, so then we can circle back to rare earth metals, because there's a specific one that I think is really interesting to talk about that I don't know a lot about myself. It's called neodymium. I think I pronounced that correctly.
That's right. Yeah, neodymium.
Cool. And I know that they're used in like all kinds of components like speakers, vibration motors, and even like the camera autofocus mechanism. So I was just wondering if you could talk about that. Seems very versatile.
Yeah, no, I love neodymium. So neodymium, it's a lanthanide. So it's one of the rare earth elements. So it's really quite an unusual element. It's quite, you don't find much of it out there. It's quite difficult to get hold of. It's not one that we are currently, struggling to get hold of. It's rare, but it's not a conflict element. So, it's actually relatively, it's okay. We're good for our neodymium, no worries there. But when you combine it with a few other metals, you end up with a compound, an alloy. Not quite sure. An alloy that is really good at being magnetized, creating magnets. So you end up with these fantastically strong magnets. So you've all seen them, neodymium magnets, and they're usually sort of very shiny on the outside. They're quite brittle. If you get two big neodymium magnets and you let go and they kind of crack together, they invariably shatter. The interesting thing, obviously, you don't get a kind of an explosion of fragments because, of course, magnetism holds it all together. So but you end up with this sort of mess of tiny little bits that you can't then pull apart because they're all kind of stuck together. And you get them in a lot of, like little kind of toys and things, sort of executive toys. But also your fridge magnets these days, most of them have got neodymiums on because your standard ferrite magnets are just rubbish in comparison. But because they're so powerful, it means that we can use them to do things that wouldn't have been possible without them. So obviously you go back to sort of, the 19th century and you've got people like Faraday and Ørsted, and they discover the electromagnetic effect. They discover that the two things go hand in hand, and we end up with electric motors, solenoids and all these sort of wonderful devices that allow us to create motion from electricity. So we've got ways of turning on and off light. We've got ways of turning on and off electricity using electricity. But now we've got a way of creating motion with electricity. And I think people don't really realize quite how many moving parts there are in your phone. And you mentioned it, the vibration alert motor is the classic moving part because it's literally a motor. It's a tiny, tiny little motor. It's about the size, if you pull open a phone, it's about the size, I reckon, of, say, a lentil. A kind of a brown lentil. So it's about 5 millimeters. What's that? Ooh, convert quickly into that's a fifth of an inch.
Oh yeah. Yeah.
No, hang on.
I think
yes.
It's another, something like that.
An eighth of an inch. Something like that. And a couple of millimeters deep, if that. Tiny little disc, usually with a little sort of rubber coating on it, with two wires coming out of it. And if you could prise it open, it's a bit tricksy, but you can. Inside, what there is there's a tiny little rotating motor. And it's made of plastic. There's usually two little coils of wire, tiny coils of wire, which create the, is the coiled wire bit of the motor. And then there is an offset weight. So that the bit that rotates isn't balanced. So when it spins around, and it spins around at a hell of a speed, it wobbles from side to side, and that causes the vibration. It's quite astonishing to see. I mean, given the weight of a phone, it's not hugely, they don't weigh much, but they still weigh a reasonable amount compared to this tiny little component. And yet that gives you the vibration alert, and you'll know when it goes off. You can hear it kind of, if it's sat on a table or something, you can sort of hear it from sort of 3 rooms away or something, this thing vibrating. And you can feel it when you're holding it quite clearly. And the only reason we can make that as powerful as it is to create that volume, or not volume, but that amount of vibration is because it's got neodymium magnets inside. There's a tiny little ring of neodymium magnet at the back, which creates the magnetic part of your motor. And you can't really pull that out because it'll just shatter, but you can sort of see that it's a magnet. If you open it up with a screwdriver, you kind of, there's this tiny little, incredibly strong magnet. And obviously the way to get a stronger motor is you either put in more voltage, or you either increase the electrical component, or you will increase the magnetic field strength. So this gives you an increased field strength, so you can do more with it. So that's in there. And, the only reason it works is because neodymium has this particular kind of electron arrangement within its structure that means it is readily magnetized. And then, as you say, you also find neodymium magnets in, they're in the, there's a little rectangular one usually in the speaker, which again is tiny compared. I mean, when you turn up your phone to full volume, you can just plonk it on the table and wander around the room and hear it. But the speaker on it it's about 1 centimeter, maybe half an inch tops, and about half that across. It's kind of a little flat job, and it's got a little tiny disc in the middle, and it kind of bounces up and down. It's an amazing piece of kit. And again, as you say, there's also ones in the camera so that you can focus the camera, which is something most people don't realize even happens.
Yeah, interesting. Is there any risk of it, I guess, like, since it's so brittle, of it breaking in any of those systems?
No, I don't think so. They're all, very well contained, and they're sufficiently small that, the little sort of metal boxes they put in then contains the magnetic field. It kind of sits within the metal coating, so to speak. So because obviously, what you don't want is kind of huge kind of magnetic fields kind of getting in the way of all your electronics. That'll stuff up your electronics. But they're shielded within the the little boxes they're put into, so to speak. So they're not going to do anything. And I've not tried pulling one out and just playing with it as a magnet, but because they are very tiny. We're talking things kind of, millimeters. Right. Tiny little magnets, but they're just wicked strong magnets. And it's all because of this wonderful material, neodymium, and a few other things they add in.
Interesting.
Fascinating.
Cool. Well, the last component we want to cover with you today is the use of plastics, and mainly in their role as a casing for our phone. So I bet the majority of us has actually dropped it. I know I do almost on a daily basis. So it's clear that casing has to be able to withstand different types of conditions. What types of plastics are the most effective choices for performance and cost perspectives, and how do we utilize those?
Gosh, that's a good question. As you say, there's a lot of plastic, there's a lot of aluminium as well goes into the casings. It's light, it's strong, it's going to survive most things that you throw at it, as long as you're reasonably careful. But then there's the plastic bits of the casing as well, they're in there. Generally speaking, a lot of the plastic, if you think about, say, an iPhone, it's almost entirely either glass or metal on the outside. There's plastics on the inside holding stuff in place a little bit. Most of us then wrap our phones in another case, let's face it, which then gives us that impact resistance. Most phones aren't built to survive drops onto, say, concrete or something like that. You can drop it on on your carpet or something like that and you're fine, but drop it onto something hard and you're stuffed, as we all know. Here's my phone. I've got it on charge. Hold on. This is my phone here. It's a Nakadell phone, and it's in the casing that it's in is actually quite interesting. As a material scientist, it's in a thing called D3O casing, which is a non-Newtonian system. So it's so if you remember your old corn flour or cornstarch mix, your oobleck as it's called by some people, it's kind of a non-Newtonian. So it becomes stiffer the more you apply force to it. You can get casings that do that. This casing, if you drop it, it becomes more rigid. I've actually been to the factory and messed around and dropped a phone from 3 meters onto a kind of a metal floor, and it survived with the right, packaging on it. Although admittedly that was with the company's PR person stood right behind me. So if it hadn't worked, would I be telling you? I would have made it out alive probably. But yeah, there are all sorts of kind of funky plastic cases and sort of cool materials that you can wrap your phone in that have remarkable properties. Wooden cases are pretty cool as well, because wood has remarkable material properties, as I'm sure you know. And as a biologist, I'm always keen to promote, but not so easy for making phone cases out of. So yes, the plastics in there. There are a remarkable number of hydrocarbons in your phone as well, all over the place. I mean, the obvious one is the screen. We've already talked about, the liquid crystal, which is a hydrocarbon, and then you've got all these other plastics and bits and bats in there, and the coverings on the wires, and your phone is full of carbon, hydrogen, and oxygen.
Yeah, I remember reading that. I think polycarbonate is a common plastic used in phones because of what you mentioned, the high impact resistance and temperature resistance. And I think that is in part due to the fact that it's a large pendant group, so that affects the rigidity and therefore the impact resistance. So it's just cool to see how the structure of these polymers play a role in their applications in the casing of the phone.
And I mean, most there's various ways you can create polarized filters as well, but a lot of them are made from kind of long chain polymers that are then just stretched as they're made, and that then lines up all your polymers kind of in straight lines, and that then creates a polarizing filter. So something as basic as that, as you're extruding the plastic or making your plastic sheeting, it's then kind of stretched as it's cooling, as it comes out of the machine, and you end up with a polarized filter. So there's all sorts of clever things like that going on there as well. It's not all kind of weird, freaky transition anthonides and actinides.
Yeah, for sure. Well, I think that wraps up all of the main subsystems within our smartphones. So I just wanted to thank you for sharing all your knowledge with us today. And I found it super fascinating. I didn't know there was all of these different types of materials and elements in our little phone that we carry around in our pocket every day.
My pleasure. Here's one thing for you to go away with. The number of elements in a phone, on average, 38.
Wow.
38.
Right, which is a third, more than a third of the entire periodic table.
That is crazy.
That is crazy, isn't it? And if you think about the number of elements in a person, only about maybe 24, and that's including some super unusual, unless of course you've just eaten a mobile phone. But but a standard person, we're not even close. The amount of sort of material science that goes into something as complicated as a phone, just astonishing. The stuff that's in there.
Wow, that's a great fun fact. I'm gonna keep that one.
David's gonna use that forever now.
He'll be dining out on that one for years.
Oh yeah.
Cool. All right, I think that wraps it up. So thanks so much, Marty.
My pleasure.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. And if you'd like to support us on this journey or simply show off your love for MSC, we actually released merchandise. And if you'd like to check out more of the designs, visit itsamaterialworldpodcast.com/shop or use the link in the description. We'll see you soon. And in the meantime, go change the world.